Okay, so I'm Wei from 1KX, and I'd like to set the context for this panel really quickly. I think one of the main risks for crypto cloud is that as we open up the opportunity to run servers for permissionless nodes, there's ability to inspect, tamper with the data that's going through these servers. And I think that's where secure computation come in. And we'll hear from our diverse set of panelists on this topic. So the first question to our set of panelists, what type of secure computation do you use? And if you can explain in simple terms what that means for your protocol. And also do a quick intro by yourself and the project. Remi, would you like to go first?
Yeah, I can start. So hi, everyone. My name is Remi. I'm the founder of Inco. So what we're building with Inco is what we call the universal confidential computing layer. And the goal here is really to basically enable confidential compute to existing blockchains. So if you look around today, all the L1 and L2s have one thing in common, is that everything is transparent. So we believe that what we're building is the fourth missing layer of the blockchain stack to really enable confidential computing capabilities to basically existing blockchains. Now, the stack we're using is actually leveraging MPC, ZK, and FHE. So each of these components have a specific role. So MPC is mostly used for decryption, ZK to prove that the FHE ciphertext is correct, not malformed, and also the user knows what the plaintext is, and then FHE for all the hidden state transition that happens on-chain. Now, collectively, these tools are very, basically to answer your question, what we think these tools enable is really the idea of encrypted states on-chain, but also state transition that can happen on top of these encrypted states in a secure manner, all by leveraging cryptography.
Chris.
Hey, everyone. My name is Chris. I'm from a fresh startup called Site AI. What we do is we are building infrastructure for decentralized secure environments by providing a separate secure computation layer, which means we have a network, an off-chain network of collaborator nodes where all the client's encrypted inputs can go into it using fully homomorphic encryption. And by computing on the decrypted data, we secure the computation itself without needing to trusting the third-party servers. As people would know, FHE, which is fully homomorphic encryption, crowned as the holy grail of encryption, would usually provide. And then all these computational tasks can be very well allocated to these computational resources off-chain, and then they will be sent back to the clients, also in an encrypted form, so that the entire procedure, on-chain, off-chain, are fully secure, keeping the privacy. And what we stand out as a startup from other FHE companies is that we combine this kind of security with, for example, like restaking as the on-chain security sense, which is the theme of today's topic, as well as verification of the computation, which is actually a very important and challenging topic in encryption world, meaning that, in addition to guarantee the privacy, we also need to verify whether a computation actually matches the demand, in the sense that, for example, if a collaboration node claims that it's using one type of machine learning model, but in reality, whether that's really using it, there needs to be a verification mechanism. And FHE doesn't really guarantee that. So we are actually solving this kind of challenges by combining a different technology to it. Thanks.
Cool. Hi, everybody. Good afternoon. It's a pleasure to be here. It's a pleasure to be with the panelists. My name is Shady El Damaty. You could think of me as a very apprehensive accelerationist. I do think that crypto economic protocols have the ability to upgrade civilization in ways that we haven't thought of before. And that's why I'm working at Holonym Foundation, why I founded Holonym Foundation along with my co-founders, to think about how we can really utilize, how we can architect trust in new ways that let us really unlock crypto economic protocols. So what do I mean by that? Well, architecting trust doesn't just mean making things trustless like we've been hearing about today. It also means taking trust and transforming it in different ways to accomplish real-world important things, right? Not just perhaps making a better way to transact or a better way to restake. There are real needs out in the world that we can solve with these tools. So how we got started actually was architecting trust for a DAO that was doing political fundraising. They took a bunch of money, but they didn't check that their users or that their DAO members were actually from the United States, so they couldn't accomplish their mission. We used CK, a form of verifiable computation, to show that each of those members within the DAO is or wasn't from the US and gated a snapshot strategy for that. That was our kind of gotcha moment. So today, Holonym Foundation does a lot more with architecting trust besides just proving identity or verifying identity. We also use multi-party compute, which is another form of verified computation, to architect trust in ways around key custody, right? So we kind of take the end-all be-all that keys today, how we derive keys, how we use keys, self-custodial wallets, is the kind of supreme summit of crypto economic technology, or just crypto in general, right? But the problem is you have to trust yourself, right? That's one of the main problems. So we solve this with MPC by taking keys, breaking them up into different pieces with little corpuscles of trust that go along with it. And we use actually Silence Labs, that you'll hear from Jay, two-party, multi-party compute as a way to do some of this stuff. And the last bit that I'll mention there is shared security is an incredible unlock for the space. What we're launching is our third product to kind of tack on and add security to the 200,000 plus CKPs that we've proven this past year, to allow users to easily derive keys from biometric low entropy data. And when you think about it from a shared security perspective, literally what you're doing is creating wallets or key architecture that's secured by Ethereum. Now you're adding demand for Ethereum, not from transactions or block space, but for security, for core infrastructure that people actually need to use Ethereum for. Anyway, that's a little bit too much, but.
Hello, I'm Jay, one of the co-founder of Silence Laboratories. We are a privacy-preserving collaboration infrastructure. We are enabling enterprises to collaborate on their secret data without moving data. That's what we are building as an infrastructure. As Robert mentioned in previous talk about data lakes and clean data rooms, that's what we are building. The equivalents of Snowflakes, Google, BigQuery, and many more, they are centralized. And we are trying to enable a more trustless approach where enterprises can collaborate without thinking about any privacy issues and compliance issues. And we do have applications of that functions in different domains. Like in threshold signing, we have in production fastest signing across the world in production right now. And in terms of general computation, we have been building compilers, which any programmers can compute and just deploy on the network and run their own data logics. Yeah.
Thanks for the detailed answers. So we've heard MPC, FHE, ZK, verifiable compute, key custody being thrown around. There are a lot of other projects out there that use these technologies, and we're at a Shared Security Summit. And so my question for you all is, where does shared security come in? And is it a key enabler for the protocol that you're building? And if so, how? And I think Shady might have already answered this question. Yeah, maybe Joe, you can go first.
Yeah. So yeah, we have been talking to lots of Web2 businesses. So as a company, we don't care about Web2 or Web3 in terms of use cases. We want to build business. So when we talk with Web2 players, the problem is they don't want single point of failure in privacy computation, but at the same point in time, they want one particular entity for accountability. There are lots of multilateral or bilateral communications which they want to avoid because that will be very slow GTM. So that's where shared security comes into picture. You have a network being run by either Eigen or Babylon's restaked, and then you have MPC on that. And then two enterprises can just plug in their data pipeline and start to compute. And this network is accountable through its economic security and restaking. And that's something which they are buying out, which I believe is a huge benefit of restaking in our sense.
You agree with that answer?
You guys already heard from me, but yeah, shared security, I think it's a huge upgrade for literally taking applications that otherwise, perhaps you would need to rely on a centralized party. Like, for example, with the wallet as a service, you're effectively putting a company as gatekeeper, a traditional web, traditional company, to access to your keys, access to your users, access to perhaps recovery methods for that. So what happens, though, when you can unlock Ethereum's security for multi-party compute networks that really, truly take you from MPC, from, say, just a consortium or just a couple nodes in a network, to MPC with Ethereum validators? So now it becomes economically attractive to run an Ethereum node, because not only are you securing Ethereum transactions in block space, you're also securing applications that are using Ethereum. So it creates this flywheel effect.
Chris, anything to add?
Sure. I would say shared security is more of a Web3 kind of notion. And since our startup is contributing as a connection between on-chain and off-chain resources, we are actually a very good example of how shared security, such as restaking, can be very well combined with other notions of security. And here, by different notions of security, I would like to emphasize on, for example, when we talk about shared security as restaking, basically it's saying we try to dramatically increase the price for misbehaving on-chain, right? So that's what restaking do in a scalable sense. Meanwhile, when we talk about security in pure encryption, that means privacy. That means you can compute on the data without seeing the content of it, without seeing the underlying sensitive information. So these are all different notions of security. How to combine them seamlessly so that users and developers can have their own choice, tune between the trade-offs, and make it as a whole solution. So that's where we stand in. One key feature of what we build is what we call Oracle contract, that site AI Oracle contract, where all the collaborator nodes, the computational nodes, they can listen to the Oracle independently, so that when you have this encrypted data come in, and the computation can be seamlessly combined with the other notions of security, so that when you have the result coming out, you don't really need to worry about, for example, if the machine learning model you're using is matching with the ones that the nodes are claiming. So you can see the different notions of behaving and misbehaving on the chain, they can be combined in one solution. A very good example in that sense is we are in a strategic collaboration with Babylon, who just gave the previous talk, where we can integrate our secure computation layer into their ecosystem. And because of the modular feature that we have, we are actually open to all kinds of this type of collaborations. So rather than just building some applications, we're actually providing an infrastructure which is open to all these kind of collaborations. Thanks.
A lot of different types of securities.
Yeah.
Remi.
Yeah, we think shared security is actually a game changer for any L1s. So we're built as an L1. Maybe to step back, why are we building as an L1? So FHE today, to do verifiable FHE, is still very difficult to achieve. So the second best option is using consensus. So now as a layer 1 blockchain, because FHE is deterministic, we can have validators sort of agree on the end result. Now, why is it a game changer for L1s? It's game changer because it solves two problems, the co-star problem of any L1s. So one, typically as a new chain, your market cap is not going to be as high, and so you have higher volatility. The idea of leveraging the asset class of ETH actually solves two problems. So one, because you're doing some kind of dual staking by leveraging different assets, you don't have to give out that much inflation. So typically you have to give out 20 to 50% as a layer 1, especially if you're a new chain. But because you're using a more mature asset class that's more stable, you can actually give out less inflation. The second problem that you're solving is really on the economic security. So by leveraging a lot more economic security on day one, so you can effectively rent a lot of economic security very quickly. And so your layer 1 will be a lot more secure since day one. instead of having to bootstrap this security throughout the process. But overall, this also solves a lot of the problems around inventory risk for a lot of the stakers. So this is also coming back to all the high inflation. So overall, we think shared security is a game changer for any new protocols that want to become a little bit more secure and mature when they launch, basically.
So it's a good way to bootstrap the network.
Exactly.
That makes sense. So I'm going to direct the conversation more towards end users. And I would say, the projects here on the panel are mostly building infrastructure, where there's, between the project and the end users, there's the set of developers that will actually build applications on top. And the question is, how does using secure computation change the developer experience? How do we make that as seamless as possible for developers so that they can actually, use this useful infrastructure to build something that's end user facing? First takers?
Maybe I'll jump in there so we can make the most use of the time. Yeah, so our AVS, it's called Mishti Network. It's named after my co-founder's cat. Don't tell him I told you guys that. But what it does is actually a pretty standard function that you find in computer science, a pseudo-random function, except it's an oblivious pseudo-random function, meaning that you can take some secret that usually you trust a server with to add some entropy to that in a trustless way, meaning that none of the parties involved in the computation know what that secret is or what that original data was. And you can use that for really cool things like taking, say, a face scan and then computing upon it locally and then sending it to this network and being able to derive a private key from that. You can also perform all sorts of role-based access control around it. So for developers, this becomes really, really interesting, especially for wallet developers, where you perhaps want to get a competitive edge, offer better UX, offer better security. You can use this AVS backend to do things like biometric gated wallet recovery, or perhaps even government ID authentication or multi-factor authentication on top of transactions that you might sign with your wallet. So yeah, there's a bunch of other pieces in the stack there, but it's really exciting because it gives wallet developers a really easy way to use, anyway, it's exciting.
Yeah, in our case, we enable confidential compute to existing blockchains. And with that, you can actually build net new use cases that aren't feasible before. So things like card games, private voting, or blind auction. So developers should care about this because historically, developers have been struggling to enable any private compute. They either have to build their own centralized infra or use more complex tools that are often difficult to learn, difficult to use. So with Inco, we can actually enable developers to just write these private smart contracts directly in Solidity on top of existing blockchains. And this is really, I would say, a 10x improvement in terms of user-developer experience as a whole. Most developers just want to, build these use cases in a painless fashion, and so this is why, the purpose of Inco, generally speaking. Yeah.
And developer just write Solidity, right? In the case of Inco.
Exactly. So, typically, new tools involve having to learn new DSLs, tooling, and so, yeah, Solidity for us, I would say, is the major advantage for, making this process a lot more simpler. Yeah.
Chris or Jay?
I think I can use one example, which we find very interesting lately, from the user viewpoint of security, as in saying, let's say, security in the sense of privacy. If we talk about privacy as in undisclosing sensitive information, such as a company's strategy or trade secrets, then people would say ZK, zero knowledge, would already be able to solve some of them. So why bother to use homomorphic encryption? And even from a marketing point of view, many ordinary users, do they really care about privacy? Do they really worry if they disclose their personal information when they're enjoying some services? In many cases, they don't really care, right? So how do we sell our story of keeping the privacy? So we find a very interesting example in, for example, gaming in a general sense. People may not really care if they disclose their information in a game, but they really care about whether it's a fair game, whether they might lose because of someone else cheating, whether they can really trust the system by betting in their own assets. So that's something they would definitely care, without any exception. And this is the notion of security that we can sell everywhere. For example, the different technologies such as ZK and FHE, they are actually complementary to each other in these different notions of security. For games where every player has full access to the information, ZK probably would solve the whole problem because the rules are transparent. And you only need to hide your strategies in the game. But if the game itself has incomplete information, then homomorphic encryption would play an irreplaceable role in it. So our startup is trying to combine these different notions of security so that we leave the choices to the developers, what kind of notion of security they need in their design. And yeah, so I think this is a good notion of security as an infrastructure.
So.
Thanks.
Would you say it's because the 0-to-1 nature of these technologies that it really enables more end users to use these applications, right? It's kind of 0-to-1 functionalities, right?
Yeah, exactly. Because it's highly modularized so that you can easily combine all these different notions in one solution.
Makes sense. Jay.
Right. So from ecosystem perspective, there are two key elements to use a privacy network. One is data, and one is very, very easy to program. So for data, we encourage all the developers to build to plug in different sources of data. We will guarantee data is never leaked, never leaves the source at least as well. But in terms of developer experience, what we have been doing is we have been building a very robust compiler. You can write a code for collaboration between two or multiple data points in Python or any other language, and the rest things will be handled by the protocol at itself. So if we can build a very robust compiler, I will imagine a day where we can build a Swift equivalent in Web3, an equivalent of anti-money laundering protocols running on these restake networks with the privacy guarantees and many more. So yeah, there's a wide open field. We just need to make the developer tooling quite well. Very easy to program in different abstracted forms.
Yeah, that makes sense. I think we are at an inflection point where shared security really enables like bootstrapping and providing better e-commerce security for secure computation, which then creates infrastructure for 0-to-1 infrastructure, 10x, better DevX for that to really build towards better crypto cloud, right? And I think our time is up. Otherwise, I will give it up to the audience for more questions. But yeah, let's thank our panelists again.
Thank you.
Thank you.